Well, I'm a little bit late, and I'm very sorry about it, but I did not realize the notes were going to actually, take me a long time. I didn't realize they were going to be, 16 pages of notes, and I waited way too long. So, this is a little bit late, but I hope this helps someone. I'm just going to go ahead and... So, I just finished the homework. Let's see, how did I even do on it? I didn't do very well on this one. That's alright. Yeah, this homework took me a long time. So, yeah, 31 questions tends to take a long time. So, I'm just going to do what I do in all of them, and I'm going to explain how I did the homework. Those of you who aren't already done with it, because it is 8 o'clock. Oh, it's all in Spanish now. Yeah. Being in Spanish class be like... Okay, so this shouldn't take too long. Honestly, the homework isn't hard. It's just 31 questions long. And the teacher made it really, really long. I would suggest you download the equations because they're useful and for no other reason. So let's just jump right into it and go with number 1. So it has, with a 1 gram sample, this is out of 86 it shows us, so 81 of 86, 0.1 grams per mole. So this is a very small part of an entire mole of hexane, whatever that is. Excess O2, so we have our chemical equation, C. Well, we don't need to write down our chemical equation because we don't care about what's coming out because it's a bomb calorimeter, so the volume doesn't change. Just the pressure, which we also don't care about. All we care about is we have we need our triangle. Let's get the delta symbol. There we go. There it is. What's that one? No idea. Anyway, we have our delta symbol, and then I believe it is... Oh, this is Q, right. So it's... I actually don't need a delta symbol, I don't think. So it's Q... I just finished the last one, so my mind is on the delta E's and the delta S's. So Q... Q cal plus... So this is our Q... So this is what we're looking for is our heat. We're looking for the heat of combustion per mole. So how much heat is produced, delta H basically, but delta H is equal to Q, and this is the equation that we have in our notes. I'm using this one. Anyway, so it's Q equals delta H, and Q for a bomb calorimeter is Q cal plus, this is Q calorimeter plus Q water, or H2O. So basically the way we find out is that all the energy from our little combusted hexane goes into the calorimeter walls and the water. So our Q calorimeter, you can see the heat capacity of the hardware component calorimeter is 4042 joules per degree Celsius. So our equation is Q cal equals C. We have our delta here. Let's go. C delta T. The C is the specific, or the heat capacity, or whatever. So it's this, 4042. And then we multiply that by our change in temperature, which is... We can go ahead and do this equation. Oh, it does that. Of course it does. So equals... So all we're going to do is multiply this by 29.3 minus 22.64. And we get in joules the heat that our bomb calorimeter received, or how much energy it received from the combustion. Next we need our Q water, which is found using the equation MCAT. Let's see, delta T. There we go. So our mass of water is 1502. We just need to follow the equation. Like, I could explain this, but basically we're just plugging in the equation. Like, I don't really know how to explain this to you. We're finding how much heat by multiplying how much heat per part of water by how much water we have, basically. It's not too complicated. I do hope you understand. If you don't understand, I'm not sure how to explain this part, because it's basically just the pool has, for every part there is one piece of heat. There are a million parts. How many heat is in the pool? A million heat. You know, like, just basically have. And then where is our? Oh right, so here we go. So if you don't understand how to put these numbers together, basically you can just look at the units, and we see we have joules, which are number we want, per grams degree Celsius. So we know we need to multiply this by joules by degrees Celsius. We have our degree Celsius, our change, our delta T is in degrees C. We have our grams of water, it's our G, and then the C is the specific heat, so it's this number. And then when you multiply this by G and degrees C, you get rid of that, and we're left with joules, which is what we want. And then it's per this 1 gram, so then we're going to multiply it by 86.1 to get our mole. And then for this one, it's saying how much heat it gets. So this is how much energy is required to heat up by 1 degree of Celsius. So if we heat it up by 3 degrees, then it'll take 4,000. It's not exactly 3. It's close to it. It's not close to it. No, it's about 7. So if we heat it by about 7 degrees, it's going to take 7 times this much energy to heat it up that much. That's basically what's going on here. So 4 times the heat change, which is 29.3 minus 2.64, and then okay, so then we add these together. So this plus that, and then we're going to divide it by 1,000 to get our kilojoules, because it's nice and easy. It's not too hard. And we get 68.77 kilojoules, but that's per 1 gram. So what we need to do is we actually need to multiply this by 86.1, because you might think at first, we need to divide by 86.1 because we have our 1 gram and we need the mole. But what you have to realize is that we're using 68 kilojoules is how much heat is produced by 1 gram. How much heat will be produced by 86 grams? You multiply it. I actually was confused about this when I first did it, but thankfully I figured it out, which is fun. So this times, and then we have 86.1. And if this wasn't so basically what we're doing here is what times 1 gram equals its mass. Thankfully, in this case, it's very easy, but later it'll actually be slightly different. So like here, so in number 2, it'll be 120 times 0.1 equals 12 grams, which is the grams per mole of carbon, which is what graphite is. It's just pure carbon. Anyway, so we got our delta H, Q, delta H, whatever, same difference, which is 5,921 kilojoules per mole. Because they're doing it they're using significant figures, so it'd be 5.92, which is number 5, which is the correct answer. Go. So for number 2, like I said, it's the exact same thing. We're just doing it with slightly different numbers. These are the numbers if you need them. You can just pause it if you need those. So we're gonna go ahead and do our Q-cal again. So heat capacity of 3 equals 344 times, that's the button, there we go. And then this is in kilojoules per degree Celsius, so that we actually don't need to divide this one by 1,000. So we'll have to divide the other one by 1,000 first before we can add them together. Or maybe it's in kilojoules, yeah, we will. We will divide the other one by 1,000 first. So 3.344 kilograms per degree Celsius. Temperature is at 0.21. So it gives us the change rather than where it goes where it comes like so that starting temperature and end temperature. Instead, it just gives us the difference. So don't do anything with this. Just multiply with this number, the 0.21 Celsius, and then. So that's our kilojoules from QCal. I'm not putting out the equation because I already put it out there. You can rewind to get it, or you can just look at your notes on them. But yeah. Anyway, so and then Q water is the 3,000 grams. So we have our mass, our M and MCAT. We have our C equals 3,000 times the C, which is for all water 4.184. And we multiply that by the delta T, which is 0.21, and we get that. That is in joules, not in kilojoules, so we will have to divide this by 1,000. And then we can add them together. This one. So this is our kilojoules, which is 3.34 kilojoules, but it is not number 2 or number 3. First, we have to multiply it by 120, because just like with this one, so I can change this to be the correct number. So we used 0.1 grams carbon, but carbon is 12 grams per mole. So to get 12 from 0.1, you have to multiply 0.1 by 120. It's not exactly 120 because it's actually 12.011, I believe, for carbon, but it's close enough, and I'm not going to multiply it by 120.1. 120.1. It's not important. So we can go ahead and multiply this value by 120. That's not what I wanted to do. Yep, there we go. There we go. So we get 400.401. It's pretty close. And because it's coming, so these are negative. So these is delta H. These are both delta H. There's no work being done. So because it's in a bomb calorimeter, the volume stays the same. So Q or delta H equals delta E because W is always 0. And so delta E will be negative because it's an exothermic reaction. So it's delta H or the Q is negative because it's losing heat. Yeah. Anyway, so this is 401. It's number 4, as you can see. Number 4. And then number 2 will be. So this is one of the ones where you flip flop them and multiply them and divide them, and they have been giving me trouble. And I have not enjoyed them, and I have made many mistakes, specifically on these I did not enjoy. So basically what you want to do is it's like doing Legos. So I want this piece. Oh, I don't have this piece, but I have 2 times this piece, so I divide this by 2. So we're going to label these 3 reactions A, B, and C. A, B, C. And then A, we want the H2. We want the H2 we want on this side, right? So we're going to flip it, so that's a negative. And then we're not sure if, because there's 2 of these and there's 3 of these, we might need a half, but we might not need a half. Maybe we need to multiply it. We don't know yet, so we're just going to leave it there. Then here, we see we need to divide this by 2, right? Because we only want 1 CH4, so a half. And then C, we have this, where is it? Yeah. We have this 2H2 plus O2 makes 2H2O. So the H2 is on this side, right? And then we're flipping this one already. This is going to be half, so I'm trying to make sure I do this right, because I know I messed up one of these in my note when I was doing homework. So we do have to flip this because we need the H2 on this side. So this will be flipped, so negative. And then we only have 1 H2 on this side, so we're going to have to half this. And since we're flipping both of these, we can see that we have one H2 because this is being halved. This isn't being halved, so we have 2 H2. So that's 3. That goes into 3 there. This isn't halved, so we have that 1 CO. That fits. This is being halved, so we have our 1 H2O going there. And then this is being halved, so we have our 1 CH4. Our O2, this is being flipped and halved, and this is being halved. So this will be half an O2, but it's be on this side, and this will be half an O2 on this side, so it'll cancel out. This one is getting flipped, so our CH3OH will be on this side. This is getting halved, so it'll only be one of them, so they'll cancel out. Okay, so yeah, this is correct. So what we need to do is our negative 128.3 will become positive, so we'll have 128.3. Our we need to half this one. Okay, so negative 328.1, and we're going to divide it by 2. And then this one is going to be positive and halved. So it's going to be 483.6 over 2. And then we're going to add these all up. Enter. So we get 206 kilojoules per mole. And then we can see it's going to be number 2. Is that correct? It is correct. Very nice. So these are just connecting the dots, really. You need only one of these, so you're going to have to half this. Have to get rid of that oxygen, so you have to flip this and half it as well. You need the one H2O, you have to flip it and half it. Like, I don't like them. I don't think it's. I think it's dumb. I really do. It's a puzzle in a chemistry class, and and then you have to do math, and it's like, oh great. Not the most fun. Not hard, just really frustrating and annoying, and I don't enjoy. And I got this wrong how many times? 2 times? 2 times, yeah. I did not have fun. So with this one, so the first one, okay, so what we can actually do, we can keep these. Really? It's... What? Did it really get rid of all my... Okay, whatever, I don't care. It doesn't matter. It doesn't matter. I don't understand Excel. Where did my history go? Anyway, so as you can see already, this is gonna get... The first one's gonna get halved. And then the second one... So we want this F2 to be there. So we actually need to multiply this by 2. That's 2. And then C... this is getting half, so we have this half O2. So this has the half O2. So, and then this has the 2 H2O, which is going to become 1 H2O. So this just needs to be flipped. Now I looked at this and didn't realize I was halving it and just halved it, and then I doubled it because I was thinking, oh no, I did it the opposite way. So I actually got this wrong twice for this exact same reason. All we're doing is flipping this one. So... I had so much fun doing this problem. Sleep full 8 hours every night, am I right? Anyway, so we're going to be dividing this one, so it's going to be equals negative 202.4 over 2, and then this one is going to be multiplied by 2, so equals, that's just negative 1200. That's not too hard. And then this one's just going to be positive 285.8. And then we're going to add them all up. These ones. Enter. And we get negative 1015.4. Negative. And that will be number 8, which is, oh, not that button. 4 is 8. Yep, there we go. I love puzzles in chemistry, am I right? They're so much fun. It's not exhilarating or scary. It's fun. You're having fun when you do these problems. Remember that. Anyway, what mass? Yes, that's the right word. Of ethanol must be burned. Supply 500 kilojoules. Okay, so when we burn a mole of ethanol, we get this much heat. We want this much heat. So all we need to do is divide how much heat we get by how much heat we want. So we want one part. So basically, we're just going to say that we're just going to divide however much the grams per mole is by this, because we divide this to get this, and this is the full. So this is what was it? Here, I can go ahead and find out. It's C2, so 2 carbons is 24 because it's 12 plus 12, plus, and we have 6 hydrogens. Each hydrogen is 1, so we have 6. And then we add our 1 oxygen. Yes, our 1 oxygen. Each oxygen is 16 grams per mole. So then we get 46, right? So 46 grams, if we burn 46 grams of ethanol, we'll get this many kilojoules. How many kilojoules will we, how many grams do we need to burn to get 500 kilojoules? So all we're going to do is divide our 46 grams by 2.736. And I didn't put the thing there that makes it actually work. There we go. Anyway, so it's 16.81 grams. You could have just kind of guessed that's about a third, but we want to do the math and be right. So anyway, so it's this one. Basically what I'm doing here is algebra, which is, I know everyone loves algebra, but here, so we have 500 kJ, small k, big J, there we go. That's an L, that's a K, that's a K, that's a J, there we go. So that's how much we want. This is how much we are getting currently, right, kJ, with our 46 grams. How many grams? So X grams. So then what you'll do in this equation is you will divide. So this is swapped with this. So then 500 is divided by that. And then you multiply it by 46. So, yeah. Yeah. What I did was I did 1368 divided by 500, and then I divided this by that instead of 500k 500 over this, multiplying it by that. But this is what I'm doing. It's cross multiplication, which is something some people really don't know how to do, which is problematic. But yeah, I'm just doing it quickly because I know how to do it anyway. Just in case you're wondering what I was doing there. We're on number 6. Yeah. Okay, so. What is it saying? Heat of formation. So what it's saying is, so this is the heat of, so this is for this, right? This is our reaction. They're saying, what is the opposite of this reaction? This is breaking it. This is burning it. What would, or however turning this into this works, it's not going to be endothermic, it's going to be exothermic probably. But so how do we? So if we flip this, if we form this out of aluminum and oxygen, so this would be negative first of all, and it's saying for 1 mole. So this number is for 2 moles. So we divide this by 2. So it's going to be negative, and it's going to be half of this. So negative and half. So it's number 1. And this is a little bit confusing because it says per mole and this is 2 moles, but it's whatever. That's the reasoning. I'm not super good at this unit, unfortunately, so it's hard for me to explain it in extreme depth, but that's what's going on there. And basically, what you can think about is that this is the same thing as having a plus as being here, and then if this is negative, then it's over here. And the reasoning for that is that this is if this is positive, it's endothermic because heat is coming in. If this is negative, then it's exothermic, right? So as we can see here, this is endothermic, right? Yes. So this would be on this side. But if it flips it, then it becomes exo. So apparently this is actually not burning. This is apparent. Oh, okay. Apparent. Oh, right. I'm dumb. When you aluminum plus oxygen is burning. It's not. It's not endothermic. I'm dumb. Anyway, so when you add them together, you're not going to heat isn't going to come in. It's going to go out. So when you burn these, you're going to get this and heat. So, and when things are exothermic, it's negative. So, yeah. Anyway, moving on. The combustion of sucrose. The carbohydrates shown as follows. So, first things first. This is WQ, delta H, same difference, and delta E. How many? So work, if you don't remember from last unit, the only time work is occurring for us is when there's a change in gas. Either there's more gas or there's less gas. There's the exact same number amount of gas moles, so W is 0. So already 2 is wrong. So we know that something is happening here, yes? We know that something is burning, it's burning, right? So delta H is going to be a number. So 4 is also wrong. So it's either, so we don't even need to do math for this one, right? They gave us the answer. So it's either negative or it's positive H. Combustion means that this number, so it says it's negative, right? Or it's negative for sucrose. But basically, if combustion is occurring, the heat is going to be over here. It's going to be negative, right? Like I was explaining up here. So if combustion is occurring, and it's on this side, and delta H is negative, only one of these has a negative delta H. So, it's 3, which we can see is right. I actually did the work for this, and all you have to do is, you do have to, that's the wrong one, look it up in your table, but that's completely unnecessary because it literally gives you the answer, because 2 and 4 are wrong, and it can only be this number, so I didn't need to. What I'm saying is probably read the answers before you do the question. But yeah, this is just do you know how exothermic and endothermic reactions function with delta H and how not having more or less moles of gas results in you having W of 0. Anyway, and next we're on number 8. So this is just another knowledge question. So basically saying if you have to form these, right, which of them will not require any energy, or which of them will not have an energy change upon formation. So if you don't remember from the notes, the only thing that is a heat of formation of 0 is an element in its natural state. Element being one element, not 2 elements. This is 2 elements, but it's the same. This is 2 atoms, but it's the same element. So you can only have one. So this could be a million fluorides, but so long as it's only fluoride, this would work. I mean, basically having a gas of fluorine, a cloud of fluorine in the air is having several trillion fluorine, but that's its elemental state. The heat of formation of something in its elemental state means that it's stable there. That's just how it comes. So it didn't require any energy or produce any energy to create that way, to be formed that way. It's formation. So there's only 2 of these which are in their elemental form. So remember, this has to be, so this is, Na is a metal. It's this metal. So with the exception of hydrogen, these are all metals. And these are all solid at room temperature, 1 atmosphere. So it has to be solid. If it's not solid, it's not going to have a heat of formation of 0. Fluorine is a gas. These are gases. And that's the way they are naturally. So it's Na and F2. If F2 was a liquid or a solid, or Na was a liquid or a gas, then it would not be 0. Or if they had other stuff attached. So number 8 is 4, which is these 2. And then number 9 is, so the balanced chemical equation is just, where did I put it? There we go. So it's, the chemical equation for this is 2Mn plus 3 halves O2 we can't, I don't care. Anyway, it makes that, and it makes Mn2O3. So I did this because I want it to be a nice 1 mole at the end, even though it's not really necessary. So what did we do in this problem? Righto. So what this is saying is that when we form this, the enthalpy is negative 962.3 kilojoules per mole. How much heat is liberated? So this is burning, because when you oxygenate something and it forms a compound with it, that's essentially combustion. It's not actually combustion, but it's combustion. Like when something rusts, it's not on fire, but the process is the same, just a lot slower, right? They're both what's the word? What's the word? Damn it. There's both spontaneous, as a fire is spontaneous once you set it alight, but yeah. Anyway, so what we need to do is we need to find out how many moles. To do that, we have to find, it tells us how many grams of manganese are oxygenized by oxygen gas. It doesn't say it's excess, but it doesn't tell us how much, so we're just assume it's in excess. So 9.3 grams, so we have 9.3 grams. The manganese, which is what this is, manganese, correct? Yes. Anyway, manganese has a weight, a grams per mole, molar mass of 54.94 grams per mole. So this will give us the number of moles. And because we're taking 2 moles and we're producing 1, we were going to have this number. Now, I see people like asking me why I did that. The reason I did that is because if 2 moles go in and 1 mole come out, if we put in 1 mole, half a mole is going to come out. If we put in 0.169 moles, then 0.84 moles are going to come out. I hope that is understood somewhat. Anyway, so we get this many moles of Mn2O3, of whatever it's called, and per mole we get this many kilojoules. So all we're going to do is multiply them together. So times 962.3. So we release, it's exothermic, 81.44 or 45 kilojoules, which is the correct answer. And then on to number 10. Will it be time for delta H for the reaction? So as we can see, more gas is being produced. If more gas is produced than is consumed, so we get more gas on the outside, that means that work is being done to push out, right? So work is being done out. It's losing energy to work. So usually, generally, heat is going to go in. So the heat is going to be positive. I'm pretty sure there's another, probably better explanation for that, but this is correct, so I don't want to crawl through my notes for half an hour to figure out the exact proper reason for that question, which is what I'd have to do if I wanted to get the exact answer for it. In this one, so it's just bonds. So it's just bonds broken in this side minus bonds formed in the product side. So reactant minus products. This is the only one where it's reactant minus products, I'm pretty sure. So see here, these are products minus reactants. These are product minus products, right? And then here it's reactants minus products, which is interesting. Just a note. So we have 4 CHs, but there's 3 CH bonds over here. So we only have a single one over here. So 416, we can go ahead and do the math for it, and it's doing that. Equals 416 plus And then we have one I8 bond. Ooh. So 151. And this is our bonds broken. It's our reactants. And then in our other side, so if you're getting confused why I said the CH3 and the CH, so there's 3 CH bonds here and there's 4 CH bonds here. We're already minusing them, and this is a balanced equation. So we just removed 3 of them from this side and 3 of them from this side is what I did. I'm saving time. Probably shouldn't do that, but 3 plus, and then we have 1 HI, so it's 299. So we just minus these, and if you can't already tell, it's 55. Yeah. So so this is delta H, right? This is delta H. Oh my god. Why you do this to me? So rude. Anyway, so this is delta H of 55, and it's positive, right? So why is it so big? I don't care. Anyway, so positive puts it on this side. That means he's going in. That means it's endothermic, which means it's 2. I got confused about this for some reason, so I got it wrong the first time. I said it's exothermic, but it's endothermic. If delta H is positive, and bonds broken minus bonds formed is equal to delta H. When delta H is positive, it goes on this side of the equation. When it's negative, it goes on this side of the equation. When heat is on this side, it's exothermic. When heat is on this side, it's endothermic. It's going in or it's coming out. It's not too complicated, and yet I find a way to screw it up, which is very exciting. Anyway, on to number 12. Oxidation of sugar to carbon dioxide. Spontaneous chemical reaction that we know spontaneous one direction currents the other direction. How can we understand photosynthesis? So photosynthesis is creating sugar using water and carbon dioxide, just if you didn't know. It's not spontaneous is the answer. Yeah. Something is doing it, so it's 5. Yeah. So something spontaneous requires that. So light is not equal to heat, not quite. It's pretty close, but not quite, because the light can be like shaded, but getting rid of all the heat is like impossible. So light is considered external agency here, and it's not spontaneous because the light is doing it. Anyway, number 13. The second law of thermodynamics requires processes generate entropy either in the system or in the surroundings. What is the thermodynamic driving force for dissolving a solid in a liquid? So basically what this is asking is, if delta H is positive, which we'll get to why that matters later, if delta H is positive, which means it's less likely spontaneous, how could something be spontaneous, specifically dissolving a solid in liquid? So I could explain it all up and down, but basically the solid is a state of order because the more ordered something is, the closer it is to something that is a perfect solid crystal and 0 degrees Kelvin, right? So if something is a gas, which is not a solid, is the farthest away from it, or extremely hot, which is the opposite of 0 degree Kelvin, or extremely not pure or perfect, like the pure, perfect 0 degree Kelvin crystal is, the further away it is from the crystal, the more disordered it is. Entropy going up is going away from the perfect 0 degree Kelvin ordered pure crystal. So the reason that solid dissolving in a liquid increases the entropy, whether of the system or the surroundings, is because the solid is becoming less ordered. Instead of being a solid, it's now basically a liquid. It's more or less, it's aqueous. It's essentially a liquid. And then it's asking here, what is the thermodynamic driving force for dissolving a solid liquid? Is that a thermal process? And it's 2. Oh, it's not. It's 4. What? Oh, I misread this because I'm stupid. My bad. Yeah, the entropy of the system is going up, like I was saying. For some reason, I misread it. I don't know. I'm tired. But like I'm saying, when you dissolve it, because the bonds of the solid are breaking, it's gaining entropy because it's going away from the crystal, which is the perfect whatever thing. I think that's the third law of thermodynamics. I don't know why that's a law. It seems like a very odd law, but whatever. So yeah, and it's the system apparently. Whatever. Look at our. So basically, what's asking here is water freezing is a decrease in entropy. It is getting closer to a perfect pure solid crystal at 0 degrees Kelvin, right? Because freezing is generally colder and more ordered and frozen and a crystal because it's ice. So how could this result in more entropy? The answer is this. The surroundings are undergoing changes. Pretty sure, yeah, this is the right answer. Just making sure, because these are... What? That's wrong. Lol. Anyway, the system is... Heat is going out, right? And because it's going out, then... I see it that way, but I don't know if that's the correct way of seeing it. But generally, when you freeze something, you're taking heat away from it. And if heat is going out of it, then it's going into the surroundings, and the surroundings getting warmer increases their entropy. So maybe it means something else, but that's how I see it anyway. When water condenses, what are the signs for Q, W, and S respectively? So water condensing is going from gas to a liquid. So that would be a negative delta S, I believe. Yes, it's a negative delta S because it's gas to liquid is a decrease in entropy. Because in order for it to doesn't it E? How does... What's the Q? The work is the work is going out, yeah? So the work would be positive? No, wait. No, okay, I remember. So we're losing gas, and because the gas is decreasing in our system, it's getting work done on it by the surroundings. So work is positive, delta S is negative, and Q, so we add heat to turn into a gas, so we have to take away heat to turn into a liquid, so Q would be negative. So Q would be so it'd be negative, positive. Wait, so just to explain it again without rambling. When something freezes or condenses, this is getting colder. It requires removing heat. Removing heat from a system, the delta H is negative. Or the Q is negative. So if you remember, like I said earlier, we consider that losing gas in a chemical equation or anything results in work being done on our system. And if we get more gas, then our system is doing work. So because work is done on our system, our W is going to be positive, and delta S, gas is less ordered. So because our system is becoming more ordered, the delta S is negative. So it's negative, positive, negative, and that is the right answer. It's hard to explain. This is really confusing. I'm not sure how I understand it as well as I do. I'm not gonna lie. Your chemistry teacher pulls up to your house and orders your family out at gunpoint, starts burning down your house. Okay, what best describes the burning of a house from a thermodynamical standpoint? You can't extinguish the fire until you tell me. I don't understand. Anyway, this is something I thought about. I'm probably way too tired of doing this. Anyway, never mind. That's not important. Anyway, it's burning, so it's exothermic, and exothermics are delta H is negative, so it's less than 0, and then the a burnt house is more disordered, so delta S is more than 0, so it's number 3. Yeah. It's such a stupid question. Anyway, for the 4 chemical reactions, which one is like? So delta S being positive in chemical reactions generally means that you're producing more gases / liquids than you are producing solids / liquids. And if you're producing more gas than you consume, or you are going from solid to gas, or solid to liquid, or liquid to gas, then that's an increase in delta S, because gases are more disordered than liquids, and liquids are more disordered than solids. And so here, excuse me. So for number one, we're losing a mole of gas, right? If we lose a mole of gas, then we're losing disorder. Excuse me, sorry. I am dying. We're losing disorder because we're losing one of our moles of gas. More moles of gas equals more disorder. So this delta S is actually negative. Here, we're gaining a single mole of gas, so our delta S is positive. Here, gas to liquid is delta S negative, and gas to liquid is delta S negative, so it's going to be number 2 only. So number 17 is 1. Number 18, so the smallest entropy, so delta S being the smallest, is going to be liquid. Like I said, liquid is a lower delta S, yeah. So here it's saying, consider the following process fuel gas ideal. The pressure doesn't have anything to do with delta S that I can see so far. Volume, however, does. Increase in volume equals delta S going up. So, which is, yeah, increase in entropy, so 2, and then temperature going up equals increased entropy, and as we can see, we only can do 2 of them, and 2 and 3 are both right, so it's 2 and 3. But also, losing energy is not an increase in entropy, and losing volume is not increase in entropy, so it's 2 and 3. So number 3, that's correct. For number 20, for the evaporation of water from an open pan at 25 degrees Celsius, the values of delta S for the water, the surroundings, and the universe must be respectively. So this is saying, so the delta S for the water is going to be positive because it's evaporating. So it's going to be positive, and then it's going to be, so the surroundings are losing energy because the water requires energy to evaporate. So it's, the delta S of the surroundings is negative, and then the universe has to be positive because the second law of thermodynamics. This is happening, whatever the word is, it's happening all on its own. Spontaneous, there's a word. I can't remember that word for the life of me. Anyway, so it's spontaneous, so the delta S universe has to be positive. So positive, negative, positive. Number 1 is correct. That is correct. There we go. So losing heat equals negative delta S. Turning into a gas is positive. And then if it's happening spontaneously, delta S universe is positive. That's not too complicated, I hope. The entropy of fusion of water is... Okay, so this one is... Okay, so basically what this is saying is we are at... So the delta G for water is 0 at 0 degrees Celsius. So this is going to be delta G of 0. But you can also calculate it, and you can see that, so 22 joules per Kelvin, negative whatever, is, so equals, and you multiply that by 273, And, well, guess what you get? You get 6,000 joules, which is just about 6 kilojoules. So if we use our equation, delta, doesn't want to type, delta G equals delta H minus, what is it, T, yeah, T delta S. So our delta S, so our entropy, is 22. We multiply that by our temperature, which is 273 degrees Kelvin. And so that's joules per mole now, because we got rid of the Kelvin. And then if we divide by 1,000, we get kilojoules per mole, which is 6,000. And we gave us our enthalpy. Enthalpy of fusion is delta H, and it's 6.01 kilojoules per mole. So we have 6 kilojoules per mole here, and we have 6 kilojoules per mole here. So 6 kilojoules per mole minus 6 kilojoules per mole is going to be 0. So our delta S is going to be 0. So this is 0 for number 21. Yeah. Number 5, yeah, 0. That one was a little bit, I was thinking, that's odd, but it makes sense to me, I guess. Let's see, number 22. What is the enthalpy of vaporization of acetone at its normal boiling point of 56.2 degrees Celsius? So, what this, okay, I don't want to get rid of it. Can I get it? Count it back? Thank you. It worked this time, thankfully. Okay, so we're doing the same thing again, but slightly differently, right? So, we have our entropy, we have our temperature, we don't have is our delta H, but we know what our delta G is. Our delta G is going to be 0 because we're at our boiling point. If we're at our boiling point, this is 0, right? And we know what our T, change that back. We know what our T is. Our T is, so it's 56.2 plus 273, so we get our Kelvin. And then we multiply that by our 88.3, our entropy, and we get this. We get 29 kilojoules. So this is how many kilojoules our enthalpy will be, because it's at the point of equilibrium. So if you add these together, they have to be 0. And if we look at, what number is this? 22? Yeah, 22. So as we can see, it's 29.1. You have to round that one up, but you divide by 1,000, you round up the 7 to 1, and you get 29.1 kilojoules. And that's our answer. And then number 23. So what this one is saying, I actually got this wrong the first time, so of course I did. Entropy change for the... So what this is saying is, for every mole, our delta H is 40,700. We have 2 moles, so our delta H is going to be that much joules. So we have 81.4 kilojoules, right? And it wants to know what our entropy is going to be. We know what temperature it is. So we have, so our delta, so this is at 100 degrees Celsius, so G is 0, right? So we can move this over here, we can add it, so we can move all our stuff around. We can have T equaling delta H over delta S, right? So we know what our temperature is, we know what our delta H is, we don't know what our delta S is. So if we swap the delta S for T, so we'll do this, so we'll have delta, oh my gosh, that's annoying. There we go. Delta S equals delta H over T. So what we can do is we can divide our 81,400 joules by our temperature. So equals 81400 divided by, as we can see, that's joules per Kelvin, right? Joules Kelvin. And we get 218.2 joules per Kelvin, which is our entropy change, apparently. I got this wrong the first time because I thought this was saying, oh, well, it's 40,000, it's 2 moles, and it's like up there. It doesn't matter. Anyway, that's how you do it. Rindlow's reaction, in which butane is formed from carbon dioxide and water. So, if it's the opposite of combustion, guess what? Things don't uncombust. Ever. So, this is not going to happen no matter the temperature. If you heat ash up to 1,000,000 degrees, it's going to burn. It isn't going to turn back into butane. And if you freeze it, it's going to be frozen ash. It's not going to turn back into butane. So no matter what you do, you can oh well, these numbers and but you can just think about this and notice that I've burnt it, right? So it's the reverse of butane combustion reaction. No, this is the reverse. So I'm not getting at... This is butane. Oh. I mean, this is this... Wait, this is not. No, this... Yeah, no, I'm right. I agree. I'm saying the right thing. I'm just confusing myself. So... Ash isn't going to turn back into butane, right? This is their ash. This is the ash, yes? This is ash, basically. It's not actually ash, but... This is what you get when you burn things. You get carbon dioxide. Ash... not going to turn back into wood by itself. So, does not occur spontaneously at any temperature. That's basically what's happening here. It's asking, can I turn ash back into wood? It will just happen. The answer is no. The answer is no, but the delta H would be, it would be positive, because it's the opposite of exothermic. Exothermic is delta H is negative, so the opposite of negative is positive. So delta H is positive, and the delta S is negative because it's becoming more ordered, and delta H positive and delta S negative means at no temperature is it spontaneous. They have a chart that they gave us, and it's what does it say? So delta H negative, delta S positive, it's always spontaneous. Delta H positive, delta S negative is never spontaneous. Delta H negative, delta S negative is lower than equilibrium temperature. It is spontaneous, and then delta H positive, higher than equilibrium temperature is spontaneous, which is really not confusing at all, but it kind of makes sense a little bit if you really think about it, but I'm not going to. So that's the reason from our notes, and I gave you the reason for myself why I think that makes sense. Anyway, the bond breaking process has delta H greater less than 0 and delta S greater less than 0. Thus it's favorable at high low temperature. So like I was just talking about the chart. So in the chart, the only way that it can be favorable at a higher or a lower, and not always or never, is they have to be both positive or both negative. So the bond. So when you have, if I recall words. Anyway, so like I was saying earlier, when you're breaking bonds to get your delta H, the reactants are on this side. So if we just have bonds breaking, this is what's happening in the reactants. Bonds are breaking. Delta H is positive for bonds breaking, right? That's a positive part of it. So delta H will be positive, be greater than 0, positive, right? Bond breaking, positive, greater. So if this is greater, then this also has to be greater, because this can't be lesser or greater when this is lesser, because then it would be never or always, and then that's not an option. So these will both be greater, and delta H positive and delta S positive is high, so it's going to be 2. So just by getting one of these, just based off how the question works, we know that it's number 2. And a better explanation of this is that breaking bonds requires energy, and forming them produces energy, I think. And energy in is delta H positive. And when you break bonds, it's less ordered. So delta S is positive. And then I don't know exactly how to I think this is just I don't know how to explain that it means higher temperatures, but that's what the chart tells me, so I believe it. So it's number 2. Yep, number 2. And then number 26. For the reaction 2C plus 2H2 makes C2H4. Delta H. Numbers. Okay, so for this reaction, we have a delta H that's positive, a delta S that's negative. So that means, according to our chart, that's never going to happen. But we're talking about the reverse. So if we reverse, if it's delta H negative and delta S positive, then it'll happen at all temperatures. So 26 is 1. Actually, I think I got this wrong the first time. Yeah, I got this wrong the first time because I didn't read the actual question. I just read this part, and then I read all the answers. I'm like, oh, it's this one. So, nope, it's number 1. Let's use our brains here. Number 27, the melting of ice is an example of a physical process. Thank you, that's very impressive that you knew that question. That can be non-spontaneous, but increasingly likely, of course, temperature increases. So it's just saying that high T, and high T is positive, and delta H positive is endothermic, and increasing system disorder. So it's number 3, and number 3 is the right answer. So, yeah. But also, delta H being positive means that heat is going in, which is what you need heat to melt ice. And when ice melts, entropy increases. So delta S is positive, and delta H means endothermic, and delta S being positive means increasing disorder. That's how that works. 28. 6 moles of gas react exothermically to yield 7 moles of gas products. What can be said about how the temperature of the reaction? This is probably annoying. I completely forgot this was on. I'll try to put something else on. Put on something that sounds better. There we go. That's probably better. Anyway, so I forgot it was on. I hope that wasn't annoying. 6 moles of gas react exothermically to yield 7 moles of gas product. So 6 moles to 7 moles means that work is being done on the surroundings. More gas is delta S positive, and I'm thinking. Let me think. What did I do in my notes? I did something in my notes, I'm sure. So I said that this was endothermic. Oh, wait. 6 moles. Oh, right. Here we go. Exothermically. How the temperature. So delta H for exothermic is negative. And because we have more gas, it's delta S positive. So negative delta H, positive delta S is excuse me. Woo. Anyway, negative delta H, positive delta S is it will always be spontaneous, which is because it's number 4. So 28 is 4. Okay. 29. Fine, come on. So the fine. So according to our chart, when delta H is positive, it is more stable and less likely to spontaneously go away. So it's going to be these two. I'm not sure how I got this wrong the first time, but I managed somehow. Anyway, so it's going to be number 2. Yeah? Yeah. Yeah. Because, positive delta H means that it requires energy to come in, and energy coming in is less likely to happen than... Well, basically, when things produce their own energy, that means they're more likely to be spontaneous, is generally what that means. Ethane is C2H6. Consider the reaction. So this one... So the formation of C2H6. Jesus. The formation of C2H6 is not spontaneous and is stable. But equally the opposite is true. But apparently number 1 is more correct. I don't totally understand this one. Why this is right and this is wrong when they're saying the same thing, but okay. I mean, it's true. The decomposition of ethane is spontaneous, and the ethane is... Oh, you know, I figured it out. Yep. Ethane is unstable because it can... Okay, I figured it out. I turned my brain on there for a couple seconds, and it worked. The reason that number 1 is right is because ethane is unstable and will spontaneously burn. Or break down, or whatever. And its decomposition is spontaneous, and ethane is unstable. Yeah, ethane is not stable. There we go. Okay. And the reason for that is delta G being positive. If delta G is more than 0, that means that it's never spontaneous this way. But the opposite way, if we flipped it, it would be spontaneous. Therefore, the decomposition, so flipping this, is spontaneous. There you go. The following statement is not correct. Delta H for a reaction is negative. The reaction can never occur spontaneously. Delta H for a reaction. So, what this is saying is, so no matter what the delta H is, just the delta H alone being negative or positive will not guarantee it being spontaneous or guarantee it never being spontaneous. So number 1 is wrong. So yeah, and 30 is 1 as well. So I'm really sorry it took me this long. I waited way too long in the notes doing the notes. It took me. I waited until today, of course, and it took me it took me like 5 hours or 6 hours or something. Those notes were so freaking long. Anyway, I hope that helped someone, and I hope you have some luck on your test. I hope I do, so I don't have to take my final, and I will see you. Maybe I'll make another one. I don't know.